Hello everyone, my name is Radhika. I am a student of Chemistry Honours first year. My roll number is 69. Today I am going to read a chapter of organic chemistry, that is structure and bonding. So now let us start. Introduction to organic chemistry. The term organic compound was originally applied to compounds such as sugar, alcohols, oils and fats, which are derived from vegetables or animal sources. That is, from living organism. This was done in order to differentiate such compound from inorganic substances such as common salt, sulfur and metals, which are obtained from mineral sources. The study of organic compounds gradually began to develop as a separate branch of chemistry which came to be known as organic chemistry. The chemistry of inorganic compounds was therefore distinguished by calling that inorganic chemistry. Vital force theory. In early days of growth of organic chemistry, it was considered impossible to prepare organic compound in a laboratory. A scientist whose name is Berzelius in 1815 suggested that organic compound could be produced only under the influence of some mysterious force existing in a living organism. This force was called vital force, and the theory of these vital force came to be known as vital force theory. However, in 1828, Waller synthesized urea, an organic compound present in the urine of animals, from ammonium cyanate, an inorganic compound obtained from ammonium sulfate and potassium cyanate. The synthesis of organic compound in laboratory shook the faith in a vital force theory. Consequently, the ideal of vital force was completely discarded by 1850, and it was formally established that formation of organic compound does not depend upon any special force. Now, let us study about modern definition of organic chemistry. Within the rejection of vital force theory, the major difference between organic and inorganic compound disappear and the term lost their original significance. But organic chemistry continued to be treated as separate branch of chemistry, although it was given a new definition. It is now defined as chemistry of a compound which contain carbon as an essential constituent. Therefore, organic chemistry can also be defined as the chemistry of hydrocarbon and their derivatives. Theoretical aspects of organic chemistry. There has been a growth of theoretical understanding in the field of organic chemistry in the last few decades. This has been very helpful in interpreting the details such as mechanism, the rate of occurrence, and the effect of temperature, concentration, etc. of large variety of chemical reactions encountered in organic chemistry. We are introducing a few relatively simple concepts in this chapter. Nature of bonding in organic compounds. The carbon atom, which have atomic number 6, which is a common feature of all organic compound, has an electronic configuration 1s2, 2s2, 2px1, 2py1 and 2pz0. This implies that carbon cannot form ionic bond in its compound and must form only covalent bonds. In other words, covalent bond is a bond of main importance in organic chemistry. According to the orbital concept, a covalent bond is formed when a half-filled valence orbital of an atom overlaps a half-filled valence orbital, that is having an oppositely spinning electron of another atom. Now a carbon atom has got only two half-filled valence orbital, that is 2px1 and 2py1, and therefore it may be expected to form only two covalent bonds. To explain the tetracovalency of carbon, it has been postulated that at the time of bond formation, the two electrons in a 2s orbital of carbon are unpaired and one of them is promoted to the empty 2p orbital in its new state called excited state. The carbon atom has a 4 half filled valence electron which would be available for the formation of covalent bonds. It may be noted that compound of 4 bonds by carbon would result in a greater lowering of energy and formation of more stable molecule than if carbon were to form only 2 bonds. This mean the this mean that even through the promotion of electron is by itself not favorable energy, it ultimately leads to greater lowering of energy by enabling carbon to form 4 bonds in place of 2. Bond energy. The process of bond formation is accompanied by the release of energy, and the bonded state represents a state of lower energy than the individual atoms. It therefore follows that an equivalent amount of energy will have to be supplied to break the bond. The amount of energy required to break a bond and separate the bonded atom in a gaseous state is known as bond dissociation energy or simply bond energy. It is generally expressed in kilojoule mole inverse. It may be mentioned that bond energy is also equal to amount of energy released when 1 mole of hydrogen atom combined with 1 mole of hydrogen atom to form 1 mole of hydrogen molecule. It is apparent that bond energy is a measure of strength of a bond. Greater is the bond energy, stronger is the bond. Factor on which bond energy depends. Size of bonded atom. Bond energy is inversely proportional to the size of bonded atom. The greater the size of bonded atom, smaller is the bond energy. Bond length. The smaller the bond length, higher in the bond energy. Smaller bond length means greater and stronger overlap of atomic orbital, which results in greater bond energy. Nature of rest of the molecule. The energy required to break a particular bond between two atoms has a specific value only for that bond and is generally termed as bond dissociation energy. But when a certain bond may be present in molecule of different substances, the actual value of bond dissociation energy of that bond will vary from one compound to the another. For instance, OH bond may be present in water as well as methyl alcohol. In polyatomic molecule, even the energy required to break a particular kind of bond may have a different values. For example, the 4 CH bond in CH4 are equivalent, but the energy required to break the first bond is not the same as the energy required to break the second bond, and so on. These differences in a bond energy of even the same kind of bond is due to the fact that the energy of a bond depends upon the nature of the rest of the molecule as well. Therefore, when giving the general value of bond dissociation energy of such bond, only the average value are stated. The average value are generally referred to as the bond energy rather than the bond dissociation energy. The values of the bond energy given in above table for HH, HCl, HBr and HI are their actual bond dissociation energy, while the values given for other bonds are average bond energies. Localized and delocalized chemical bond. Localized chemical bond. When a chemical bond is formed by an overlap of two atomic orbitals, the orbitals that result are the property of a chemical bond, not of the individual atom. That is why the resultant orbitals are known as molecular orbitals. The electron in this orbital are shared between the atoms involved in a bond formation. For example, let us consider the example of formation of hydrogen molecule from two hydrogen atoms, each having one s electron with antiparallel spin relative to the other. When the 1s orbital of two atoms overlap, The two 1s orbital become paired and begin to occupy the same molecular orbital. The probability of finding these electrons is greatest in the region between the two nuclei. It is due to concentration of negatively charged electron between the two positively charged nuclei that the two nuclei are bonded together. It may be pointed out that even though both the electrons are negatively charged, they tend to concentrate in an internuclear between due to their antiparallel spins. Therefore, the two paired electrons are said to occupy a localized molecular orbital, and the bond formed is known as localized bond. A localized bond may therefore be defined as a bond whose electrons are greatly concentrated in a region between the two nuclei only. Delocalized chemical bond. To understand the delocalized chemical bond, let us consider the case of molecule containing double bonds and the single bonds in alternate position. Double bond which alternate with the single bond are said to be conjugated. For instance, 1,3-butadiene is a conjugated diene, while 1,4-pentadiene is a non-conjugated diene having isolated double bonds. Let us now discuss the molecule of 1,3-butadiene as a typical case of the formation of a delocalized chemical bond. Each of the four carbon atoms of 1,3-butadiene is in a sp2 hybridized state, having 3 sp2 hybridized orbital and 1 unhybridized p orbital. The 3 sp2 orbital of each carbon are used in a formation of sigma bonds with adjacent carbon and hydrogen atom, and all these bonds are localized bonds. However, if a molecule is a planar, then the p orbital of a carbon can also overlap the p orbital of another carbon, just as it overlaps to the p orbital of any other carbon. This means that there is overlapping of p orbital of C1, C2 and the C3. In this condition, we do not have pair of electron mainly confined to the region between two nuclei. In other words, the bond formed are no longer localized. Therefore, a molecular orbital which is spread over the nuclei of more than two atoms is known as delocalized molecular orbital, and the electron present in it is termed as delocalized electrons. The bond thus formed are a delocalized bond. Effects of delocalization of bonds. The delocalization of bonds has the following effects on a system involved. Effect on the bond length. The formation of delocalized bond causes the bond length to change from the normal value of single, double and triple bonds. For example, the bond lengths between two adjacent carbon atoms in a 1,3-butadiene neither correspond to the carbon-carbon single bond length nor carbon-carbon double bond length. Second one is effect on molecule movement of electrons. In delocalization bonds, the electrons have a greater freedom of movement than in a localized bonds. Effect of stability. Delocalization of bond leads to the decrease in energy of the system. Kinds of molecule which contain delocalized bonds. Double or triple bond in a conjugation. Apart from 1,3-butadiene discussed above, benzene is another important example of molecule containing multiple bond in conjugation which exhibit delocalization. All the carbon atoms of benzene ring are in a state of sp2 hybridization. The three hybridized orbital of each carbon involved in the formation of 3 sigma bonds, 2 with adjacent carbon atom and 1 with hydrogen. Thus, the odd electron in an unhybridized orbital of each of the 6 carbon atom from pi electrons cloud involving more than 2 atoms. In other words, the pi electrons are spread over or extensively delocalized, and this results in the formation of a molecule containing orbital embarrassing all the 6 carbon atoms. Second one, double or triple bond in a conjugation with a partial p orbital on an adjacent atom. The presence of a p orbital, which may have two, one, or no electrons, on an atom adjacent to the multiple bond also leads to the formation of a delocalization bond. For example, vinyl chloride. Allylic carboanion afford another example of a structure exhibiting delocalization in which p orbital on an adjacent atom to multiple bond contain two electrons. Hyperconjugation. This type of delocalization involves carbon hydrogen sigma bonds adjacent to the multiple bond and is discussed later in the section 1.8. Next one is van der Waals interaction, intermolecular forces. Intermolecular forces are the attractive forces which operate between molecules of the same or the different substances. For instances, in covalent compound containing polar bonds, partial negative and the positive charges are produced on atom by unequal sharing of electron pairs. As a result, majority of these molecules passes a dipole moment. However, non-polar molecules also have a weak intermolecular forces as discussed below. Non-polar molecules such as oxygen, nitrogen, chlorine and methane exist in a gaseous state in form of individual covalently bonded molecules. But even such substances as well as noble gases undergo condensation at low temperature to liquid and solid state, which is accompanied by decrease of energy. This leads to the suggestion by van der Waals, a Dutch physicist, that there must be some weak intermolecular interaction between such molecules which become relatively stronger in a liquid or a solid state. They may be defined as very weak forces of attraction between non-polar molecules which arise from a movement of electrons in an atom and a molecule. That these forces are quite weak is evident from the fact that non-polar molecule substances and noble gases have a very low boiling points. This can be possible only if intermolecular forces are weak and are overcome by supplying very small amount of energy. Origin of the van der Waals forces. To understand the origin of these forces, let us consider two helium atoms very close together. Ordinarily, in each atom, the charge of the electron is symmetrically distributed around its nucleus. However, since the electron move about freely, we can imagine that at a particular instant of time, the second distribution in atom becomes somewhat unsymmetrical with a slight increase in electron density on one side. Therefore, for a very small fraction of a second, this atom has one and very slightly negative related to the other end. This temporary separation of a positive and negative charges produces an instantaneous or temporary dipole. The temporary dipole in a turn influences the electron distribution of another atom present in a neighborhood because the negative end of atom repels the electron of an atom. Although this picture persists for an extremely short time and the momentary and induced dipole are constantly changing, the net result is force of attraction between the neighboring atom. The forces of attraction between non-polar molecules due to temporary dipole-induced dipole interaction constitute van der Waals interaction. They are also known as London forces or dispersion forces. Next topic, factor influencing van der Waals forces. First one, number of electron in the molecule. The magnitude of van der Waals forces depends upon the number of electron in atom or a molecule. With the increase of number of electron, there is more chances for the electron distribution to become unsymmetrical. Size of the molecule. As the molecule size increases, the surface area becomes large. Consequently, the chances of unsymmetrical electron distribution increase and the van der Waals forces become stronger. That is why the boiling point of a series of a similar compound generally increase as a molecular weight increases. Third one is a molecular shape. The weight of van der Waals forces, the magnitude of van der Waals forces also depend upon the shape of a molecule. To illustrate this statement, let us consider the case of N-pentane and neopentane. N-pentane is a straight chain having a large surface area, while neopentane is a compact molecule having much lesser surface area. Hence, the magnitude of van der Waals forces is very small. That is why neopentane has a much lesser boiling point than N-pentane. Fourth one is a temperature and pressure. It may be also noted that for the same substance, the van der Waals forces are relatively stronger at low temperature and high pressure. At low temperature, the random moment of molecule increases with provide greater opportunity for molecular interaction. Naturally, therefore, the van der Waals forces are relatively stronger. Types of van der Waals interaction. It may be pointed out that apart from the intermolecular forces between non-polar molecules due to temporary dipole induced dipole interaction, the term van der Waals interaction also include the following type of attractive forces. First is dipole-dipole attraction and second one is dipole-induced dipole attraction. The dipole-dipole attraction, as already stated, these are forces of attraction which operate between molecules which are permanently polar in nature, such as HCl, NH3, SO2, and acetone. Dipole induced dipole attraction. These forces operate between molecules, one of which is polar and other is a non-polar. Under the influence of polar molecule, a temporary dipole is induced in a non-polar molecule. Van der Waals repulsions. The magnitude of van der Waals forces of attraction increases as the distance between the non-bonded atom or a molecule decreases. The attraction becomes maximum when the distance between the non-bonded atom or a molecule reaches a certain minimum value. This minimum distance at which the force of attraction is maximum is equal to the sum of van der Waals radii of non-bonded atom or molecule. If the non-bonded atom come so close to each other that the distance between them is lesser than the sum of their van der Waals radii, the attractive interaction turn into repulsive interaction. Resonance. It has already been studied in earlier class than the concept of resonance or mesomerism was put forward to explain the structure of compounds such as benzene. It has been suggested that if a molecule can be assigned two or more conventional valence bond structure, each of which can explain most but not all the observed property of a compound, the actual studies lied somewhere in between the various possible conventional structure. The various possible structures are called contributing or canonical structure, and the actual structure is called resonance hybrid. The concept of hybridization of two or more conventional valence bond structure to arrive at an entirely new and individual structure, which however cannot be depicted on a paper in terms of conventional formula, is termed as resonance. One of the most known example of application of resonance is afforded by benzene. This implies that the structure of benzene is represented by either one, not two, but lies somewhere in between the two. It is evident that in resonance hybrid, the bond which link the carbon atom neither correspond to single nor double. On the other hand, all the bonds are equivalent and are intermediate between single and double bonds. The resonance hybrid structure of benzene has 151 kJ mole inverse of energy less than the either of the contributing structure. These represent the resonance energy. Other example of resonance: carbon dioxide. Carbon dioxide is considered to be resonance hybrid of three contributing structure as shown below: carboxylic acid, 1,3-butadiene, and etc. Now let us study about condition for resonance. According to the general theory of resonance, the various conventional structure formula contributing to the various structure of resonance hybrid must satisfy the following condition. That is, the number one, the various contributing structures should differ from each other only in the position of electron, whereas the relative arrangement of atom and their state of hybridization must be the same. Second one, the atom involved must lie in a same or a nearly the same plane. Number 3, the number of paired and unpaired electron in each contributing structure must be the same. Number 4, all the contributing structure must show the correct number of valence electrons. Number 5, all the contributing structure should have the same or the nearly same amount of energy and stability. Number 6, when the contributing structure different in a energy content or relative stabilities, the more stable structure makes greater contribution toward the resonance hybrid. In determining the relative stability of contributing structure, large the number of the covalent bond in a structure, greater is the stability. Second one, the structure involves separation of positive and negative charge are less stable than those which do not involve any separation of charges. When atoms of different electronegativities are involved, the structure having negative charge or more electronegative atom and a positive charge or less electronegative atom are relatively more stable than the other. The structure having like charges on adjacent carbon are highly unstable. The more the number of contributing structure, more stable is the resonance hybrid. Now the properties of a resonance hybrid. Stability. A resonance hybrid is always more stable than any of the contributing structure. Resonance energy. It is a measure of stabilization due to resonance and may be noticed and defined as the difference in energy between the energy of a resonance hybrid and its most stable contributing structure. Bond length. In a resonance hybrid, the bond length are different from those in a contributing structure. It may be seen that the concept of resonance hybridization is essentially equivalent to the delocalization of electrons. Therefore, the term delocalization energy is often used in place of resonance energy. Resonance effect. It is a process of permanent displacement of electron in a molecule brought about by resonance or a mesomerism, generally designated as R or M effect. For this reason, it is also termed as conjugative effect. What happened is that resonance effect causes delocalization of electron and give rise to a additional contributing structure due to withdrawal or release of electron by a given group. Types of group involved in resonance and their resonating effect. Group having electro-withdrawing resonance effect -R or -M effect, like NO2 R C double bond O R, cyano group SO3H and C double bond O R. Group having electron releasing resonance effect positive R and positive M. It is important to remember that unlike inductive effect, resonance effect suffer practically no decrease in intensity with the number in distance along the chain of atom. Application of resonance effect. Low reactivity of vinyl halide and aryl halide. As compared to alkyl halide, vinyl halide exhibit low reactivity in nucleophilic substitution reaction. Similarly, low reactivity of aryl halide toward nucleophilic substitution can be explained in terms of resonance stabilization. Second, acidity of carboxylic acid. The acidic nature of carboxylic acid is due to ionization or aqueous solution to form carboxylate ion and hydronium ion. Therefore, carboxylate ion is stabilized by resonance due to greater extent than carboxylic acid, which explain the tendency of a carboxylic acid to undergo ionization. We will encounter many three example of resonance effect in explaining the case of formation of relative stability and relative reactivity of many species during the course of our study.